now on, let's talk about the extension of the model. Well, most of things are same as what we have discussed with linear regression. So nothing much is difficult, and nothing is very different from what we have discussed. So let's briefly look at and let's try to recall the idea. So the first one is online gradient descent. In other words, stochastic gradient descent. So well, there was some cases where you could feed in only one instance at a time. So there was a modification for linear regression problem where we have same modification for logistic regression problem. So J09 is defined as what we built in the previous slide. So only difference is instead of giving the batch of the data set, you are going to provide only one instance at a time. And based on that, you could use the same updating rule as well. Only difference is you're doing this for every other instance. So you need to be careful in choosing this learning rate alpha. Other than that, we're basically same as updating of logistic regression gradient descent. So nothing should be very difficult. And this is the modified algorithm for logistic regression. Again, most of the things are the same. Only change is the updating rule over here. And now let's think of some cases like this. Let's think about what a linear classifier can do and cannot do. So in data set like this is what logistic regression can perform very nicely. So we can draw some decision boundary like this. It should be straight line. So this line is representing WTX is equal to 0. And if you have W, you can easily determine the class membership of your test data. But in this case, there could be a no straight line that classifies blue and red dots perfectly. So you can try something like this, something like this, something like this. All of them cannot be performing in a complete manner. Well, the reason why this cannot perform a perfect classification is the decision boundary is nonlinear. And again, our model is based on simple linear combination of input. So linear model cannot perform well on nonlinear problem. And for this case, we use the same expansion as we did with linear regression. So simple expansion is using the feature function. So this phi applied to x will generate some additional features based on the original input. So this is your original input and get expanded based on the feature function phi. And based on this expanded feature, where you have new W, and the rest of the model is the same as the regular logistic regression. And let's move on to regularization. So regularization, the idea here is to prevent the model from being too complicated. So let's remove some of the input variable to the model by setting some of the W value close to 0 or completely 0. So in order to make many of the weight value or unnecessary weight value close to 0, we want to use L2. So the J function over here, basically the same, only difference is here. So you are adding one additional regularization term. And L1, this guy, makes unnecessary W equivalent to 0. So here is the updated J function. And this is the last component associated with logistic regression. And this is a sort of new expansion that we haven't discussed with the linear regression. So this is an expansion to multi-class classification. So far we talked about binary classification where the number of classes is 2. So this is indeed a special case of multi-class classification. So multi-class classification, we have number of classes larger than 2. So in this illustration, binary classification were simply represented in 2 colors. Multi-class classification is represented in 3 colors. So well, you can get the idea simply, right? So out of this data set, we want to draw some sort of perfect diagram of regions. So this is the area of blue, this is the area of red, this is the area of green, sort of, and make a decision based on that kind of specification. So there are two approaches mainly used in multi-class classification. So one of such approach is one versus rest approach. The other is one versus one approach. So in both cases, the idea is to use binary classifier to handle multi-class classification problem properly. This is the goal. And the first approach, one versus rest approach, here we split a multi-class classification problem into multiple binary classification problem. So we want to build one model for one class. So basically we are building a classifier determining class 0 or class 1 or 2. So we want to build a model that draws this line, class 0 and the rest. The second model, this guy classifies class 1 versus class 0 or 2. So you want to draw this line. And the third model determines between class 2 versus class 0 or 1. Class 2 versus 0 or 1.
So if you have this set of classifiers, you can easily make a multi-class decision.
But even after you have this collection of classifier, you still have problem. So anything goes to this side where you can think of blue. Anything goes to this side, you can think of red. Against this border, anything goes to this side, you can think of green. But if you do so, there are some ambiguity because this area hasn't been claimed by anyone. So this is something called as a region of nobody. Because none of the classes claimed this is my territory. And some area in between like this, where this is either blue or green. Well, same thing is happening in this block, class red or class green. Here as well. So these regions are called as ambiguous region. So these are the logical issues when you have three different classifier to make a multi-class classification solution. And one of the remedy is to use the property of logistic regression. So logistic regression is returning you the confidence of the decision. So based on the confidence that you can estimate from the model, where you can maximize that quantity. So from now on, we can build a decision rule like this for multi-class classification. So GC, the determinant function for class C, that is representing this value. So this is coming from individual model, and you want to maximize this quantity. And if you do so, well, you can redraw the decision boundary as you see on the screen as a yellow line. And this addresses the issues that we had before. And let's move on to one versus one approach. So one versus one approach splits multi-class classification into one binary classification for each pair of the classes. So let's think about the class pair. So there are three possible pairs. So let's simply take these two classes and build a binary classifier. So class 0 and class 1, you can build a model that draws this line. And for class 0 and class 2, that are red and blue, so you can build a model that draw this decision line. And class 1 and class 2, that's between green and red. So you can build a model like this. Well, if you draw decision boundary in this way, again, this is a logically valid idea, but still you have a problem where this area, in the middle, this is claimed by all three classes. So where this is again quite ambiguous to make a decision. So this is called as ambiguous region again. And one remedy is to define a new discriminant function by adding the individual discriminant function that we obtained in the previous case. So GC over here, where for each class that you want to build a discriminant function on, you want to sort of marginalize it on the other classes and take the summation. So you can define a new discriminant function in this way. And again, you want to maximize this quantity. If you do so, this small area on the screen, where this can be magnified in this way, and you are going to divide this small ambiguous region into three classes. So, like we have seen both one versus rest or one versus one approaches. They define a multi-class classifier using multiple binary classifiers. So we have seen different issues that can come up with. So region of nobody, that is the territory that is not claimed by none of the classes, and ambiguous region, so that is territory claimed by two or more classes. So in order to handle that issue, we defined some additional discriminant function and sort of reviewed the maximizing decision rule. Still, we have additional issue that we haven't discussed there. So that is called that calibration. So calibration in general means something like this. So you have logistic regression function, and this gave you some probability. The question is this probability estimate correct? So calibration is a task to adjust the probability estimate to return more accurate or more precise probabilistic estimate. So that is what calibration is for. Where the problem is where we built those probability estimator independently. So you have three different functions, class 1 versus 1 or 2, function versus 1 or function 2 versus, or something like this. That means you have three different logistic regression. The question is the probability estimate from the first guy is compatible with the other guy. And there is no clue because, basically we don't have any ground to say the probability estimate from this guy is compatible with this guy or the other. So, this is an unsolved issue. And one of the solutions is to train those three models jointly. So, some of you may heard of softmax function. Softmax function is from the design of it, it is to jointly run multiple logistic regression function. So using some sort of internal marginalization, it is controlling the weight vector of each different W. But that's sort of brief idea, where understanding this issue in terms of multi-class classification expansion, that is enough for our course. This is sort of everything that I prepared for today. If you have any question, let me know.